So yes, sir. So one of my friends actually dropped the fourth. So should I grab here? Thank you. So hi, my project is based on visual haystack problem. So I'll briefly describe what the problem is. So in the LLMs can perform a task of putting the images, and we can query the images and find the object or any relevant query. So what the problem we have seen is that after a number of particular number of images, the performance of the LLMs drop drastically. So we are trying to solve this problem by few methods. So here's the content what I'm presenting. There are two papers. So the first one is supervised metric learning for rank retrieval via contextual similarity optimization. So till now, what the problem was in the previous research that contextual similarity problems they were having overfitting problems and they required large amount of data to train. And so um, and many metric loss functions focuses on the correct ranking of the samples, and there was no connection between the model and the loss function itself. So this new approach, which is given by the author in the paper, is more robust to overfitting and also requires less data compared to previous research. So what the problem the paper the problem to that was proposed in the paper is that let's consider there are two pictures of uh, animals there which seems to be very similar to each other. Like there is a white neck raven and a common raven. If we put these images in a ResNet like architecture, it would give very close embeddings, right? But but these are two different classes. So the model would be confused as if this is the white neck raven or this is the common raven. So the paper is trying to increase the embedding space of these two embeddings so that they can be classified easily. So how are they? Okay, and the results which they have proposed actually performs better than every other solution that they have compared with. Okay, so what did they do different? So most of the techniques optimizes cosine similarity only. They did use contextual similarity to find the loss, but they did not propagated that loss back into the uh, uh, network. And this is because the contextual similarity is actually non-differentiable, so the getting the gradient and that is actually difficult. So they have solved this problem in this paper, and this indeed gave them a better improvement compared to other metrics. Okay, so I'll explain what the mathematics is. So let's consider that there are two samples I and j, and the I have its positive samples and the j has the negative one. So the maths which the paper proposed is like this: that let us consider the ith sample, and let's say that I'll take the closest four samples and create a boundary out of it, and then I'll of course take a constant e to actually make it a more expand the boundary a little bit more, and then this function uh, one nke plus e is actually finding how is the sample in the neighbor of the other sample. Like, is the j in the neighbor of the sample I? So this is what it is calculating. It is based on distance. Okay. And then they have defined over with this respect, they have defined two other variables, m plus and m minus. So m plus and m minus are the variables which are counting how many neighbors are in the neighborhood. Like the m plus is counting how many neighbors are in intersection with both the sample I and j, and the m minus is counting how many neighbors are not in the sample of I and j. That is just minusing what is in the intersection of those. And then they have putting that in the variable in this equation, and they are getting a weighted m1. Hi. So yeah, so in the initial steps, they are just calculating how many neighbors are in common both the samples. Like the I and j, we'll count how many what samples are common in both. Like the plus and the minus, we'll count all of those, and we'll also count how many are not in those intersections. I'll get to that. Like it will be helpful in later stages, like getting the similarity between the samples. No. Hmm. Point is known. Yeah, yeah. The point is known, like how many neighbors are to each. What neighbors does that point have? That is what matters here. Like even the positive samples and the negative samples, like different classes. It will help in the. I'll explain how it will work. Okay, so this is what we have got W1. Till here, the author has calculated W1, and now the author is using a step, defining a query expansion step. That is in this step that let's say that the sample A has the closest nearest neighbor B and C, and B has A and D. So now we identify the reciprocal similarity. Like A and B are reciprocal neighbors, like both consider each other neighbors, and A and C are reciprocal neighbors. Okay. So now the author is calculating W2, that is to identify all the reciprocal neighbors of A with respect to B and C and how this works. So we'll average the similarity of these. So now we'll average the similarity of this with respect to a third neighbor, that is D. So how we'll calculate is that we'll take W2. We are calculating D with respect to A. So A has reciprocal similarities of B and C. So we'll calculate the W1 of D with respect to B and with respect to C, and we'll just average them out and we'll get a value. This is 0. Over here we are getting an example as 0.45. And then we'll compare this with the true labors which were given in the like we will compare this with a true labor for the training step. Okay. Any questions though? So hmm. No, not yet. Like this is just like a neural network. This is the predicted value, and then we'll compare this with the original value. Like if it is in the neighbor, like if A and D are in the neighbor, then it would be 1, and if it is not, then it would be 0. Then we will do that. Okay, so now I'll explain the optimization step, how the author has optimized this thing, like how they have given the intuition of this mathematics. So, okay, let's say that W1, the equation which we have taken, we'll just value them, we'll just take the constants out, and then we'll differentiate that function, and we get two equations from these. Okay, so the first equation is just the normal uh, pairwise equation, which is responsible for the correct ranking of the samples, like which will come higher in the order. And the next two are the other important ones. Like these two will define how far the sample would be. Like let's say the sample I has to move away from it. So these two equations will govern the movement of I with respect to all the samples of J. Like all the samples that were in the class of J. It will move away from the I, and same will happen for the J. So this is the intuition which they have given in the paper. Uh, so yeah, so why this matters in the paper is that they give a they create a semantic consistency in the embedding space, and by considering the neighbor and not just the individual pairs in it. And of course, the traditional lossy just pushes I and J apart, but here they are pushing I and all the samples of J apart together. Yeah. Mm. Right. So. Mm. What else is lost? Mm. Right. Mm. So here we are actually moving the we are picking up one sample and we are just moving it away from all the samples of J itself. Like uh, in in classical clustering algorithms, what we do is like we take a sample and we see how far it is from the other classes, right? But here we are pushing it away all at the same time. Like the all the samples of Y are getting pushed away from all the samples of J at the same time, not individually. So they are kind of it is being helpful in some way. Not so, not really. Okay. Mm-hmm. Okay. Mhm. So, okay, let me just get this a little clear. Are you saying that there's a class and there's another class? Class one is having all the nodes connected to each other, and so is the second class, right? Are the nodes in the class itself changing its distance with each other or not? In one class, yeah, in one click, zero distance. No, 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 no. Yeah, you can say that. Hmm. No, they are changing. They are changing. Like in here, del of the first equation itself is actually changing the distance of it. It is increasing the embedding space between each sample, increasing the embedding distance. Yeah, that is what the point is. Because if they would be far apart, then it would be easier to classify what class are they in. Because it's 2M. Hmm. I mean, they will also, they would be close to each other, but they would be at different distances. They might be different distances. They would be far away from the other class, but they would be close to each other, but might be at different distances. Okay. Okay. Yeah. Any questions? Okay. So yeah. So yeah. So this method actually gave a better result than the roadmap MS minus methods, and this they have tested this method out, and uh, it is actually performing above par with every other method there. So okay, so I'll explain the experiment. So they are using a resonate architecture, resonate 50. They are creating the embeddings, and then they are of course using this contextual loss function to increase the embedding space. Okay, and then they're testing how well these embeddings are. Yeah, they are finding. I mean, of course, in the name itself, they are finding how similar these are to each other and how different they are to each other, and then they are increasing the contextual space to classification and other methods. Mhm. Okay, so there is a data set they have provided which has birds like the CUB data set. They have birds, animals, and other classes. They have very different. Yes, yes, there is a class label. They are not like it is not unsupervised. It is actually having labels at the end. Yeah. So yes, of course, this is performing above par with every other the baseline. Hmm. Right. So the point which you are putting, like we can just regularize that points out. So they have also defined if you want to get the state of the art result, we can actually huh, like a model which can be used or anything else. Okay, so I think the baseline could be the model itself which we are using, and then I mean we are getting the embedding space. They are already at distance with each other. Like we are using different classes to train, which are alternative to this. So yes, sir, I'm um hmm, yes, sir, I didn't. Um, okay, so I can at the point think of a model itself, not training the pre-trained model. Okay, we can we can take a pre-trained model like Resonate 50 and make another model like a linear model itself, and then we can train that model to actually just increase this thing and the embedding space. Yeah, yeah. Be one approach. Not to increase the distance between. Acha, okay. Mhm. No, no, no. How like okay, Hmm. Yeah. Okay. Huh. Like what will I do with this thing? Okay. Okay. Uh, what I am thinking is we have the embeddings, right? So and similar looking classes like objective will have similar looking embeddings, right? They would be close to in space with each other. And if you want to classify better, then we can actually change those embeddings that they would be different from each other. Like I mean, I'll like far apart in the embedding space. Like two different classes would be far apart in the embedding space. Take a model, right, and make a simple neural network itself, and then use this loss function to train that neural network itself and nothing else. That's it. And then we'll just class classes which were defined previously. Like yeah, just train to classify. That's it. Because but like if there is a good boundary between those two. Hmm. I have not compared them. So the papers. Yeah, yeah. These are two data sets. Acha, the R1, yeah, triplet loss. Yeah, yeah, yeah. I got actually take three pairs, anchor and a positive and a negative pair. I guess that's what it does. Yeah. Because here is not just an anchor, it is just taking all the classes, all the samples at once, and then yeah, that is what my understanding has came from the paper. Okay, I actually got confused. Okay, okay, okay. So yeah, so the conclusion of for this paper is so if you want to get a better performance than just contextual, you can just combine this with the contrastive loss, and you can get for the state of the art performance on some data sets. So so yeah, and this function actually reduces the overfitting problem and the embedding space for context consistent similarity. Okay, so now this is the second paper which I am presenting. It's understanding deep contrastive learning via the coordinate-wise optimization. So in this work, the author has provided a new way of contrastive learning, and uh, and it has also given relations between the neural network and the loss itself. Because before this, there was not much studies happening what the features the model was learning with respect to the contrastive learning, contrastive loss. So okay, so we can so this is the table of contrastive loss. We can these are two functions. We can form these contrastive losses by while taking these pairs of loss functions. Okay, so the problem like no now focus on loss function. Okay, I have explained this. And also, the paper also analyzes non-linear networks, like how the ReLU networks with respect to contrastive learning works. And of course, there is a limitation to this. We are not able to learn beyond layer of ReLU network, and learning understanding beyond that is actually problematic, if not hard. Okay, before I start with the presentation, I'll just explain what the author has taken the argumentation samples as in, like the xi dash. Those will be coming in the paper. So what the author has done is that they have taken an original image and then they have cropped out and resized part of it. So for the paper itself, they have just taken the first two argumentation, but we can do every other. So they've also said that if this is the original image, let's say the sample I, these two argumentation will become its positive samples. And we'll do the similar thing with the other pictures, and those two will become the similar samples for that and negative samples for this one. Okay. So this is the general loss function of contrastive loss. We can, of course, from the table itself, we can take the phi and the psi value, and we can form a contrastive loss function here. Okay, so the finding in the papers which the author proposed that let's say there is an energy function which is defined as the trace of contrastive covariance matrix, and after doing the mathematical differential derivatives, we have found that the loss function, the derivative of the loss function with respect to the parameters of the model, is the same as the negative. Is this like if I say it in a more mathematical way, the gradient descent of the loss function is same as the gradient ascent of the energy function. So this is like they have proved this formula in the paper. But this is E alpha I've shown here. They have the trace. They have defined this energy function as such. Okay, okay. So alpha, okay. So the alpha is the parameter that is given to the samples in how weighted those samples would be. Like, okay, can I use the board? If let's say there is an anchor here, okay, and there is a sample here, and there is a sample here. So the alpha is assigned in a way that how far these samples are to each other. The sample which is closer to the anchor itself will have a higher alpha value, and the one which is far away will have the lower alpha value. Okay, so this is how the alpha is defined, and the z which is defined as this, the z is just the output which is we are getting from the deep learning architect or deep learning model. That's it. Yeah, the alpha will change with, but further in the paper will also say. Yeah, they have. Yeah, I'll explain that they have given. So this is the first finding of the paper, and yeah, they have proved that there is, if we take this as an energy function, this would be true for it. The equation or the value of psi as an exponential function, then there are some pairwise importance to alpha which will come. Like in the minimizing problem, we can have alpha as the reduction of the energy function or a derivative of the energy function minus the regularization. And so they have provided a constraint over here that like if we take this constraint, then we can actually get the values of alpha with respect to the energy function. Okay. And in the influency solution which they proposed, that the constraint over here was alpha with this, like this is a distance function. Okay. So with this constraint, if with this constraint we take alpha, then we can say that after a particular value of distance, like I have explained over here, the value of alpha would be such insignificant that we can just neglect that sample in the training step itself. So this is just that is represented. Okay. So that was they won't be as much important in the training because they are so far apart that it won't make much difference to it. Okay. Okay, so now so the author has now proposed how we can minimize the loss function. Okay, and this method will actually propose a new contrasted learning function method itself. So the author has said that we can get the values of alpha by minimizing the energy function and taking a regularization of it, and we can change the parameters of the model by just taking the derivative of the energy function. Okay, so this mathematical way actually proposed a new method of alpha CL, which actually performs well with the other loss function like the quadratic and the NCE loss function. This was performing better, so they have proposed a solution. So, any questions still here, sir? Okay, so now I'll. Yeah, this is some. Huh. Yeah, by such like I mean, of course, we can just take the distance, see the distance, how far they are. We get the value of alpha. Okay. Okay, so now the paper comes to a different section of the mathematics and all, and they give a representation of how a simple linear layer with this energy function actually converges to a PC solution. So now we have understood what alpha and how the energy function changes with respect to the parameters, and uh, so yeah, and of course, like. Hmm. Okay, so yeah, so now we are pulling in some constraint on the weight. We have taken a neural network, simple linear neural network, and we are putting some constraint on it that the weight of that simple neural network would be like W and the W transpose of it would be equal to the identical matrix. Okay, and then we are forming the energy function. We are getting the energy function as such that uh, we are getting this energy function after reformulating all the things. We are okay. So So from this, we just found that though we found like the contrastional deep learning networks is essentially the reparameterization of PCA. So, so like, and okay. So we found the solution that it is equal to PCA, but there is one thing that this solution which we are getting from here, this actually gives the negative eigenvalues because of course there are negative argumented samples. So this is giving some negative values, which is not in uh, which is not there in the PC in traditional PC. Okay, so this is one backslash of this. But yeah, it is giving giving a proper PC solution to it. And yeah, and this is just the reparameterization PC. They have just defined this thing that with this approach, we are just reparameterizing the PC approach. Okay, so now let's talk about if we put a ReLU network, like an activation layer between these things, and how would that change? They have defined samples as orthogonal samples and one hot encoding, and the augmentation is just the like we can take a gamma value of I and just change that. It is not like just a scaling of that, and like intuitively with so yeah, so like this solution also seems to be really identical to the previous solution, but the dynamics is same as the linear counterparts, but it is like important. So there are some important modification to it. Like the weight of these networks actually normalized to 1, and from this solution we will get the direction of the solution to the maximum eigenvalue of that PCA solution which we were trying to get. That is an assumption. We are taking that, okay, this is the X input sample, this is the out, this is the argumentation. We're changing the inputs over here. Yeah, it is the paper talked till then there, and this is the new section they have started. So okay, so unlike the linear network, the relevant networks follows a modified gradient flow where if the weight goes to 0, then like the sticky effect prevents the certain weights from changing itself. And overall, the simple case of getting a local optima in a simple linear layer changes here. Like we can just now get different, like more than one optimal solutions over here. So yeah, this was just increasing one layer of ReLU network, and if we keep on increasing these layers, the dynamics become impossible to predict how things happen, and we won't be able to analyze what is happening in the network itself. Yeah. And okay, so project description, I'll explain what it is. So like what the team is thinking is that we'll take a pre-trained model. Yeah, I'm by myself and my TA. That's it. So what we are thinking is that we will take a model itself and we'll create a simple neural net model. Okay, and of course we have studied how the contrastive loss and contextual losses are working, and they are increasing the embedding space and they are giving much better classification. So we are trying to find a new loss function, you can say, that will be helpful in training. So that is what our project description is. Under the similar settings, yeah, contextual with respect to the contextual, like how the gradient changes and all. Yeah, yeah, yes. Okay. Okay, so like we are trying to improve that classification thing itself. So yeah, improve the classification thing. Yes, you can say this. Yeah, we can. Hmm. Right. Okay. Any questions?